Imagine a world where giant creatures could crush entire forests with a single step. Some were smaller than your dog, while others towered into the skies. This was a land of mystery, danger, and unstoppable power. Every shadow hid a predator, every breath carried fear, and every day was a battle to survive. If even a single moment of this thrilling, awe-inspiring history lodges itself in your mind, I'd love it if you hit that subscribe button, give a like, and drop a comment telling me where in the world you're watching from. Sharing these ancient secrets with history lovers from every corner of the earth is what truly excites me. My dear friends, before we begin this history, let's take a moment to see what topics this entire story will cover. Where dinosaurs lived, why it matters, continental drift, climate zones, and how geography shaped dino diversity. Origins of dinosaurs, early Triassic beginnings, the first species, and the garage band of dinosaurs. Dinosaur evolution, how different lineages emerged, adaptive innovations, and parallel evolution. Dinosaur extinction, theories, asteroid, volcanoes, climate change, and ecological collapse. The dino family tree, theropods, sauropods, ornithischians, and their fascinating connections. Size, shape show-offs, from tiny Compsognathus to gigantic Argentinosaurus, evolution of extremes. Anatomy, physiology, skeletons, muscles, feathers, and the mechanics of movement. Behavior, habits, daily life, hunting, foraging, migration, nesting, and survival strategies. Communication, noise, roars, calls, posturing, and what fossils tell us about social behavior. Love, eggs, reproductive biology, courtship rituals, nesting grounds, egg laying, and parental care. Predators, prey dynamics, top predators, prey adaptations, and the ultimate arms race. Research discoveries, fossil digs, famous paleontologists, and breakthrough discoveries. From myth to museum, how dinosaurs captured human imagination, myths, and modern exhibitions. Dino legacy, birds, feathers, DNA traces, and their impact on modern science and culture. Rise, fall of dinosaurs, round 2, final reflection on their 165 million year reign and the lessons for Earth's future. Alright, friends, let's not waste any more time. Let's begin, right from the very start. Imagine a world unlike anything we know today, a planet with no cities, no borders, no roads. The Earth was a place of raw power and constant change, a living, breathing entity in motion. During the Mesozoic era, some 250 million years ago, the continents as we know them did not exist. Instead, there was a single colossal landmass, a supercontinent called Pangaea. Picture it, a gigantic expanse of land stretching across the equator, its center searing hot, its edges frosted by ice, and constantly shifting under the restless movements of tectonic plates. This was a world in upheaval, a stage set for the rise of the dinosaurs. Pangaea was the ultimate experiment in isolation and connection. While all the land was technically joined together, vast deserts, mountain ranges, and inland seas created microenvironments, pockets of life that evolved almost independently. Here, in these scattered ecological theaters, dinosaurs began to experiment with life itself. Each region would become a crucible for adaptation, forging creatures uniquely suited to the climates and challenges around them. Let's drift across this ancient world. In what we now call South America, the story of dinosaurs truly begins. Around 230 million years ago, in the late Triassic, some of the first known dinosaurs roamed the dusty plains. Herosaurus, a slender, predatory dinosaur, sprinted across the fern-covered landscapes, hunting, hiding, surviving. Alongside it, Eoraptor, one of the earliest omnivorous dinosaurs, scurried through the underbrush, a reminder that life in the Mesozoic was not just about size, but about cunning and speed. South America was, in a sense, the garage band of dinosaurs, the place where experimentation started, where the early notes of evolution were first played. As we moved northward, Pangaea's vast expanse allowed different evolutionary experiments to occur. What happened in what is now North America? Here, the landmass provided a mosaic of environments: coastal plains, river valleys, and inland forests, each offering different challenges and opportunities. Dinosaurs that emerged here were adapted to hunting in open spaces or hiding in dense vegetation. The isolation caused by mountains and inland seas meant that even though these continents were joined, the populations began to diverge, slowly but surely. Meanwhile, in what would become Africa, deserts and seasonal climates shaped an entirely different set of dinosaurs. Large herbivores evolved to survive in harsh conditions, developing long necks to reach high vegetation, or defensive armor to protect against predators. Predatory dinosaurs in these regions became masters of ambush, relying on stealth, strength, and coordinated hunting strategies. Geography dictated not just where dinosaurs lived, but how they lived, how they moved, how they hunted, and how they avoided being hunted. Australia, at the time, was connected to Antarctica as part of the southern supercontinent Gondwana. Here, the cold and temperate climates created another distinct ecosystem. Dinosaurs evolved unique strategies to cope with these conditions, from migratory behaviors to burrowing habits. The polar regions were not lifeless wastelands as one might imagine. They were homes to thriving communities of dinosaurs adapted to months of darkness and harsh winters. The very idea challenges our perception of dinosaurs as purely tropical, sun-loving giants. It's important to realize, as we drift across this ancient world, that dinosaurs were not evenly distributed. They were not scattered like sugar over a cookie. Instead, geography, climate, and the slow march of evolution produced pockets of life, some small, some immense, some delicate, some terrifying. Isolation was a driver of innovation. Mountains became walls, rivers became highways, and oceans became barriers. Species evolved in parallel, sometimes producing similar adaptations in completely separate regions, and sometimes producing marvels completely unique to their home. Take Europe, for instance. It was a patchwork of islands, emerging from the shallow Tethys Sea. Here, smaller, agile dinosaurs thrived, developing intricate social behaviors and complex hunting strategies. The fragmented landmass meant that populations were often confined to a single island, a natural laboratory of evolution. Over millions of years, the dinosaurs of these islands developed traits not seen anywhere else, a delicate reminder of how place shapes life. And then there were the oceans. Though they were barriers, they also allowed for the distribution of species across distant lands. Some dinosaurs, especially the smaller, more versatile ones, could exploit coastal environments, moving along shorelines and occasionally crossing land bridges that appeared during periods of low sea level. The ebb and flow of seas, the rise and fall of land, all dictated the rhythms of life, survival, and extinction. The climate zones themselves were a major force. Pangaea's interior was a scorching desert, inhospitable to most life, while coastal areas were lush and green, rivers carved deep valleys, and monsoon-like weather patterns influenced vegetation cycles. Dinosaurs had to adapt to these conditions. Some became migratory, following the rains. Others evolved features to conserve water or to endure long periods of heat. Every scale, feather, or spine told a story of adaptation to the land beneath them. As continents slowly drifted apart, beginning the breakup of Pangaea around 200 million years ago, the stage was set for new ecosystems to emerge. Dinosaurs that once shared the same land now faced isolation. North America, South America, Africa, Europe, Asia, and eventually Australia became cradles for unique evolutionary experiments. The very separation of land masses intensified diversity, producing some of the most spectacular adaptations in dinosaur history. And yet, geography wasn't just about survival. It also influenced behavior and social structures. Some dinosaurs developed herding behaviors to navigate dangerous landscapes, while others became solitary hunters, perfecting ambush tactics in dense forests. Rivers, lakes, mountains, and coastlines were not mere scenery, they were characters in the drama of life, shaping diets, migration patterns, and even reproductive behaviors. Every fossil we discover today is a snapshot of this interaction between dinosaur and environment. The bones tell us about size, strength, and diet. The sediment tells us about climate and vegetation. The very placement of fossils across the continents reveals the hidden maps of ancient migration, adaptation, and survival. Without understanding where dinosaurs lived, we cannot truly understand who they were, what challenges they faced, and why they evolved the ways they did. And so, as we drift across this ancient earth in our imagination, we begin to see a pattern. Place matters. Geography dictated not just the species of dinosaurs that existed, but the possibilities available to them. It shaped their forms, their behaviors, their relationships with one another, and their ultimate fates. From the scorching deserts of Pangaea's heart to the icy edges of southern Gondwana, every region was a stage, every valley a theater, and every mountain a sentinel of evolution's ongoing drama. It is astonishing to realize that these creatures, so different from anything we know today, were so intimately tied to the land beneath them. Their evolution cannot be separated from their environment, their survival cannot be divorced from geography, and their story cannot be told without tracing the movement of continents, the rise and fall of seas, and the shaping forces of climate. So, as you imagine these ancient lands, allow yourself to drift. Picture Herosaurus sprinting across a South American plain, Eoraptor darting through underbrush, and the first theropods stalking the edges of rivers. Visualize the polar forests of Gondwana, the scattered islands of Europe, the deserts of the Mesozoic interior, all connected by the slow dance of continents and climate. The stage was set, the actors were ready, and the world itself was both canvas and character in the epic story of dinosaurs. Let's take a step back in time, farther than any human could possibly imagine, to a world just beginning to recover from one of the greatest catastrophes Earth had ever seen. The Permian-Triassic extinction, a devastating event some 252 million years ago, had wiped out nearly 90% of life on the planet. Imagine landscapes stripped bare, skies thick with ash, oceans boiling and churning, and yet, in the aftermath of this chaos, life found a way. Slowly, persistently, the first hints of a new era began to emerge. This was the dawn of the Triassic period, a world of experimentation, adaptation, and quiet innovation. It is in this raw, fragile world that dinosaurs first began to carve out their place. The continents had already begun their slow drift. Pangaea still stretched across the equator, a massive, unified landmass, its interior a furnace of deserts, and its edges fringed by rivers and forests. Life here was sparse, but it was resilient. Small reptiles dominated the landscape, many of them far more nimble than their predecessors, evolving new strategies for survival. These early dinosaurs were not the titans that would later dominate the Jurassic or Cretaceous. They were small, scrappy, fast, and cunning, the ultimate garage band of the Mesozoic, tinkering with the first riffs of evolution's song. In what is now South America, some of the earliest dinosaurs began to emerge. Herosaurus, often considered one of the first true theropods, prowled across floodplains and fern-covered plains, hunting insects, small reptiles, and even fellow early dinosaurs. Picture it, a sleek, agile predator, no larger than a modern-day horse, moving with precision and cunning. Alongside it, Eoraptor, one of the earliest omnivorous species, scurried through the underbrush. A reminder that adaptability was key in this chaotic world. These creatures were experimenting with diets, hunting strategies, and locomotion, each small adaptation a step toward a future dominated by giants. The Triassic period was a time of experimentation on an unprecedented scale. Dinosaurs were not yet the rulers of the land, they were opportunists, taking advantage of niches left vacant by extinct species. While many large reptiles still roamed the planet, crocodile-like predators and sprawling amphibians, the early dinosaurs were quietly evolving traits that would set them apart. Light, hollow bones allowed for speed. Sharp teeth hinted at diverse diets. Strong hind limbs and flexible tails enabled agile movements through ever-changing landscapes. Isolation played a critical role. While the continents were connected, geographical features, mountains, rivers, and deserts, created pockets where populations could evolve independently. This parallel evolution allowed different species to explore different experiments in survival. In one region, dinosaurs became swift hunters, in another, small, cautious omnivores. Across these pockets, evolution was conducting multiple trials, and only the most adaptable survived. North America tells a similar story, though with its own unique twists. Inland basins and river valleys provided shelter from harsh deserts, offering vegetation and water that supported early dinosaur populations. Species that emerged here were slightly larger, taking advantage of more abundant food sources. They began to display early social behaviors, hunting in pairs, scavenging in small groups, and even perhaps warning one another of dangers lurking in the shadows. Geography was again shaping life, dictating not just where dinosaurs lived, but how they interacted, hunted, and survived. Meanwhile, Africa, still joined to South America and Antarctica in the supercontinent Gondwana, offered its own ecological challenges. Early dinosaurs here were forced to survive in seasonally harsh climates, with dry periods alternating with wet monsoons. Herbivores experimented with feeding strategies, reaching higher foliage with longer necks, while predators refined stealth and speed. In many ways, Africa was the ultimate testing ground for evolutionary innovation. It is fascinating to imagine the size of these early creatures. Most were modest by later standards, some barely 2 to 3 feet long, but what they lacked in size, they more than compensated for in adaptability. Every bone, every muscle, every movement was part of a trial in evolution, testing the possibilities of life in this new Mesozoic world. Their success was not immediate. For millions of years, dinosaurs remained a background presence, quietly shaping the trajectory of life, while larger reptiles still dominated the stage. Behavioral adaptations also began to appear during this early phase. The need to evade predators and survive in harsh climates encouraged early dinosaurs to explore bipedal locomotion, giving them the ability to run faster and maneuver more efficiently. Some may have been able to climb over rocky terrain or move through dense underbrush with greater agility than their competitors. In short, the first dinosaurs were survivors, engineers of evolutionary solutions that would later allow them to dominate entire continents. Their reproductive strategies were also evolving. While evidence is scarce, paleontologists have inferred that early dinosaurs likely laid eggs in hidden nests, carefully choosing locations that provided both safety and warmth. Some species may have even exhibited rudimentary forms of parental care, guarding their eggs against predators, an early hint of the complex behaviors that would appear in later dinosaur lineages. Fossil evidence tells us more than just size and shape. It reveals movement, behavior, and diet. Fossils of Heterosaurus and Eoraptor, for example, show evidence of sharp teeth adapted for slicing, while hind limbs indicate speed and agility. These bones are not just remnants of life, they are snapshots of survival strategies, adaptations, and evolutionary experimentation. They tell us that the first dinosaurs were clever, versatile, and constantly testing the limits of what life could achieve in a post-extinction world. As the Triassic period progressed, the first dinosaur lineages began to diverge. Theropods, like Heterosaurus, pursued predatory strategies, becoming agile hunters. Sauropodomorphs, early ancestors of the massive long-necked giants, experimented with plant-eating, exploring herbivorous niches that had been largely empty after the Permian-Triassic extinction. Ornithischians, though smaller and less numerous in the early Triassic, began exploring defensive adaptations, from thicker skins to early forms of body armor. Each lineage was conducting its own evolutionary experiment, and the results would set the stage for the Jurassic explosion. And yet, despite their innovation, these early dinosaurs were not invincible. They shared the world with formidable competitors, giant amphibians, crocodile-like predators, and other reptiles that had survived the extinction. Survival required not just strength, but ingenuity. Those that could move faster, feed smarter, and adapt more quickly had a distinct advantage. Natural selection was relentless, and the Mesozoic world was both teacher and test. The garage band analogy is apartment. These early dinosaurs were experimenting, testing evolutionary rifts, trying out combinations of size, speed, and diet. Some failed, vanishing from the fossil record. Others succeeded, laying the groundwork for what would become one of the most dominant groups of animals in Earth's history. Just like a band starting out in a small garage, Their performances were modest at first, but the potential for greatness was already written into their DNA. Across continents, the rhythm of evolution continued. South America, Africa, and what would become Europe and North America each hosted their own experiments in survival. Species adapted to deserts, forests, and floodplains. Some became specialized hunters, some nimble omnivores, and some cautious plant eaters. Geography, climate, and competition dictated the pace and direction of their evolution, ensuring that by the end of the Triassic, the stage was set for the rise of the giants. And so, as we imagine these small but incredibly adaptable creatures moving across a recovering, reshaping world, we begin to understand the true significance of their origins. They were survivors of chaos, innovators of life, and the first notes in an evolutionary symphony that would play for over 165 million years. Each sprint across a fern plain, each cautious hunt along a riverbank, each careful choice of nesting site, contributed to the incredible success story of the dinosaurs. This is the world of the early Triassic, the beginning of the dinosaurs. Not yet kings, but quietly, relentlessly experimenting, adapting, surviving. They were small, agile, and ingenious. They were the garage band of life, playing the first notes of a song that would echo through the ages. Setting the stage for an era of giants, of predators and prey, of triumph and extinction. And as you imagine their lives, their struggles, their tiny victories, allow yourself to drift with the rhythm of evolution itself, the slow, persistent, unyielding march of life that would eventually lead to some of the most extraordinary creatures to ever walk the earth. Dinosaur evolution, how different lineages emerged, adaptive innovations, and parallel evolution. The Triassic period set the stage, but it was during the Jurassic and into the Cretaceous that dinosaurs truly began to diversify, exploring every ecological niche imaginable. Evolution was no longer just about survival. It became a complex dance of adaptation, experimentation, and sometimes sheer ingenuity. Across the drifting continents, different lineages began to emerge, each carving out a unique place in a world that was constantly reshaping itself. Theropods were among the most remarkable of these lineages. Starting from small, agile hunters like Herosaurus, they gradually evolved into a variety of forms, some no larger than a modern dog, and others towering over 40 feet tall. Their adaptations were both physical and behavioral. Hollow bones made them lighter and faster. Sharp, serrated teeth allowed them to exploit different diets, while variations in claw structure enabled precision hunting or climbing. Eyes positioned forward gave stereoscopic vision, turning these predators into highly effective hunters, capable of stalking, ambushing, and chasing prey across diverse terrains. Parallel to the rise of theropods, sauropodomorphs were experimenting with size and feeding strategies. Starting as small bipedal herbivores, they gradually evolved into massive quadrupeds like Apatosaurus and Brachiosaurus. Long necks allowed them to reach the highest foliage, exploiting food sources unavailable to other herbivores. Skeletal adaptations, such as massive vertebrae and robust limb bones, provided support for enormous weight, while tail structures offered balance and, in some cases, defensive capabilities. The evolution of sauropods illustrates one of the most dramatic examples of adaptive innovation. When the opportunity to dominate a niche arose, life responded with breathtaking scale. Ornithischians, the bird-hipped dinosaurs, evolved along a different trajectory. Small and often armored, they explored defensive adaptations, from bony plates to spikes. Over time, this lineage gave rise to some of the most iconic species, stegosaurs, with their towering plates and spiked tails, and ceratopsians, featuring frills and formidable horns. Their evolution was shaped not only by predation pressure but also by competition for food. Parallel evolution is evident here. Across separate continents, similar adaptations appeared independently, highlighting the powerful role of environmental pressures in shaping form and function. Even within these broad categories, evolution was experimenting with innovation on a smaller scale. Feathers, for example, first appeared in some theropod species, likely as insulation or display features before they were co-opted for flight in avian lineages millions of years later. Beaks appeared independently in several ornithischian species, allowing for efficient cropping of vegetation. Tail clubs, armor, and specialized teeth all demonstrate the diversity of adaptive solutions that evolution produced in response to specific challenges. Geography played a central role in shaping these evolutionary experiments. As continents drifted apart, populations became isolated. North America, Europe, Africa, South America, and Asia each hosted their own unique evolutionary laboratories. In North America, vast floodplains and river valleys allowed some species to grow massive, while smaller species explored agility and speed. In Asia, diverse climates from lush forests to arid interiors encouraged a wide array of adaptations, producing species like the feathered velociraptor and the gigantic sauropods of the Gobi Desert. Africa's seasonal and arid environments drove yet another set of innovations, with some species developing defensive armor or efficient migratory strategies to cope with changing resources. Parallel evolution is one of the most fascinating aspects of dinosaur evolution. Across separate continents, unrelated lineages sometimes developed strikingly similar traits. Long necks appeared in sauropods on multiple continents independently. Defensive frills, plates, and spikes evolved in different ornithischian species. Even predatory strategies converged. Small, agile hunters on separate land masses evolved similar body plans, sharp claws, and keen senses. This convergence highlights the fact that evolution is both inventive and constrained. It finds similar solutions to similar problems, regardless of location or lineage. The fossil record also reveals bursts of innovation, periods when new traits and forms emerged rapidly, often in response to changing climates, the availability of new food sources, or the extinction of competitors. For example, the early Cretaceous saw an explosion of ornithischian diversity, with specialized herbivores exploring niches from forest undergrowth to open plains. Theropods concurrently diversified, some evolving into apex predators of unprecedented size, while others refined agility and intelligence. Sauropods continued to push the boundaries of size and feeding strategy, often coexisting with large carnivores in complex ecosystems. Behavioral adaptations co-evolved with physical ones. Social structures became more complex. Herding behavior, seen in sauropods and some ornithischians, likely provided protection against predators and facilitated migration to track seasonal food supplies. Predatory tactics evolved as well, with some theropods hunting in coordinated groups, relying on strategy and cooperation to capture prey. These behavioral innovations were as crucial to success as physical adaptations, and they demonstrate that evolution shapes not only bodies but also behavior and social interaction. Climate fluctuations, volcanic activity, and tectonic shifts created new pressures and opportunities. Rising mountains, shifting rivers, and fluctuating sea levels altered habitats, creating isolated regions and forcing species to adapt or perish. In some cases, isolation led to dramatic changes in size, from dwarfed species on islands to colossal giants in vast continental interiors. Evolution is a slow, iterative process, but these geological changes accelerated the pace, opening new niches and encouraging experimentation. It's also important to recognize that evolution was not linear. Lineages sometimes split and rejoined. Some traits disappeared only to reappear millions of years later in different species. This back and forth, trial and error nature of evolutionary innovation allowed dinosaurs to explore a vast array of forms and functions. Teeth adapted, tails thickened, limbs elongated, and sensory organs refined, each modification a response to immediate environmental pressures, yet also a step toward future possibilities. Feathers, again, are a striking example. Initially likely for insulation, thermoregulation, or mating display, feathers eventually became central to flight in birds. This innovation began in small theropods during the Jurassic, illustrating how a single trait could have far-reaching implications millions of years later. Similarly, the evolution of complex dental structures in herbivorous dinosaurs allowed them to exploit previously untapped plant resources, demonstrating how adaptation opens entirely new ecological niches. Some lineages evolved unique defensive strategies. Stegosaurs plates, ankylosaurs armor, and ceratopsians' horns evolved independently in different lineages, highlighting both convergent evolution and the intense pressures of predation. Predators, in turn, refined hunting strategies and body plans to counter these defenses. This evolutionary arms race pushed both prey and predator to innovate continuously, resulting in some of the most visually striking and functionally sophisticated dinosaurs to ever walk the earth. The fossil record also hints at experimentation in sensory perception and intelligence. Evidence suggests that some theropods had keen vision, acute hearing, and perhaps even complex problem-solving abilities. Such traits would have enhanced hunting success and survival, influencing social behavior and communication. Meanwhile, herbivores may have developed early warning systems, herd coordination, and other strategies to avoid predation. Evolution was shaping minds as well as bodies. Even reproductive strategies were subject to experimentation. Some species appear to have laid eggs in hidden nests, others in communal nesting grounds. Egg size, clutch size, and nesting behaviors evolved in parallel across continents, again showing how similar solutions arose independently in response to ecological pressures. Parental care, hinted at in some fossilized nests, further illustrates how evolution explored behavioral as well as anatomical innovations. The continuous branching of lineages, the appearance of novel traits, and the adaptive exploration of ecological niches culminated in the incredible diversity of dinosaurs we associate with the Jurassic and Cretaceous periods. From tiny, feathered hunters to massive long-necked giants, from armored stegosaurs to horned ceratopsians, evolution produced an astonishing array of forms. Each lineage, each species, was an experiment, some fleeting, some enduring, all part of the grand evolutionary narrative. And through it all, parallel evolution remained a defining feature. Across separate continents, unrelated species repeatedly arrived at similar solutions: speed for predators, armor for prey, elongated necks for feeding advantage, specialized teeth for diverse diets. Evolution was both creative and practical, finding the most effective designs to meet the challenges presented by geography, climate, and ecological competition. Even small details mattered. The position of limbs, the shape of claws, the development of sensory organs, and even the arrangement of feathers were all part of an intricate system of adaptation. Every modification increased the chance of survival, allowed species to exploit new resources, or enhanced reproductive success. The Mesozoic was a workshop of life, and evolution was its tireless craftsman. By the mid-Cretaceous, dinosaurs had filled almost every terrestrial niche. Herbivores grazed on plains, browsed forests, and munched aquatic plants. Predators ranged from stealthy stalkers to towering apex hunters. Evolution had explored forms, behaviors, and strategies in ways that would set the stage for millions of years of ecological dominance. Dinosaur extinction, theories, asteroid, volcanoes, climate change, and ecological collapse, time flows, continents drift, and millions of years pass, yet the dinosaurs, creatures that had dominated Earth for over 165 million years, faced a challenge unlike any before. The Mesozoic era, which had seen the rise of immense sauropods, cunning theropods, and intricately armored ornithischians, approached its final act. Life had adapted, evolved, and flourished, but the balance of the Earth was shifting, and with it came forces that would forever change the course of natural history. Scientists today point to multiple, sometimes overlapping explanations for the sudden disappearance of dinosaurs. The most famous and dramatic of these is the asteroid impact. Imagine a celestial object, kilometers in diameter, hurtling through space at unimaginable speed. Roughly 66 million years ago, this massive body struck the Yucatan Peninsula in present-day Mexico, creating the Chicxulub crater. The energy released was equivalent to billions of nuclear bombs detonating simultaneously. Fires erupted across continents, shockwaves tore through the crust, and dust and debris were ejected into the atmosphere, blotting out sunlight. The consequences of such an impact were catastrophic. Photosynthesis faltered, plants withered, and the food chains that depended on them collapsed. Herbivorous dinosaurs, once abundant and thriving, struggled to find sufficient nourishment. Carnivores, reliant on these herbivores, faced starvation. Temperatures plunged initially due to the dust cloud blocking sunlight, followed by a period of intense heating from the fires and atmospheric changes. The impact itself was instantaneous, but its ecological ramifications persisted for years, pushing the planet into environmental chaos. Yet, the asteroid was likely not acting alone. Massive volcanic eruptions, particularly the Deccan Traps in what is now India, released staggering volumes of lava, ash, and gases over hundreds of thousands of years. Sulfur dioxide and carbon dioxide poured into the atmosphere, causing acid rain, ocean acidification, and long-term shifts in climate. Seasons became unpredictable. Oceans warmed or cooled in sudden cycles, disrupting marine ecosystems. On land, droughts and floods became more frequent. Dinosaurs that had survived asteroid events previously would now face a planet where resources were uneven, water scarce, and habitats fragmented. Climate change, both gradual and abrupt, also played a significant role. During the late Cretaceous, sea levels fluctuated, creating shallow inland seas, altering coastlines, and reshaping ecosystems. Average global temperatures rose and fell, forests shifted to grasslands, and deserts expanded. Such environmental volatility stressed ecosystems, weakening populations and making them more vulnerable to sudden catastrophic events. Species that could not adapt quickly enough to these changing conditions found themselves teetering on the brink. Ecological collapse was another critical factor. As food webs unraveled, competition intensified. Herbivores competed for dwindling vegetation. Carnivores struggled for prey, often turning on weaker members of their own kind. Smaller mammals, birds, and reptiles that could burrow, fly, or exploit alternative food sources fared better, hinting at why some lineages survived while others vanished. Dinosaurs, often large, highly specialized, and dependent on stable ecosystems, were particularly vulnerable. Their evolutionary success, honed over millions of years, could not withstand the rapid convergence of asteroid impact, volcanic activity, and climate instability. Fossil evidence supports these theories. In the layers corresponding to the K-PG boundary, paleontologists find sudden die-offs, disrupted ecosystems, and dramatic changes in flora and fauna. Iridium, rare on Earth but abundant in asteroids, appears globally in this layer, corroborating the impact hypothesis. Lava flows, traceable over hundreds of thousands of square kilometers, provide a record of prolonged volcanic activity. Plant fossils show abrupt shifts in composition, consistent with climate-induced stress. Together, these data paint a picture of a planet in turmoil, struggling to sustain its once dominant inhabitants. Consider the cascading effects. When plants die, herbivores starve. When herbivores decline, carnivores follow. Microorganisms and insects also experience upheaval, further destabilizing ecosystems. Rivers and lakes may have become oxygen depleted, forests burned or drowned, and weather patterns thrown into chaos. These pressures did not eliminate species evenly, rather, they created a sieve, filtering out those unable to cope with rapid environmental change. Dinosaurs, remarkable as they were, could not survive the convergence of these catastrophic forces. But extinction was not instantaneous everywhere. Some regions may have remained habitable for a short while longer. Isolated islands, deep forests, or remote floodplains might have offered temporary refuges. Fossils from these areas suggest that dinosaurs lingered longer in certain pockets, but ultimately, the global network of stressors caught up. Survival required adaptability, mobility, or simply a measure of luck. Mammals, small reptiles, birds, and some amphibians demonstrated these qualities, slipping through cracks in the ecological collapse, while even the mightiest theropods and sauropods vanished. The asteroid, the volcanoes, the climate shifts, they were not isolated phenomena. They intersected, amplified, and compounded each other. A volcanic eruption could destabilize local climate, weakening populations already stressed by shifting ecosystems. The asteroid impact, arriving suddenly, compounded the pressure, leaving little room for recovery. Earth's biosphere, finely balanced yet fragile, could not absorb the shockwaves of these converging disasters. dinosaurs, despite their evolutionary sophistication, were not equipped to endure such rapid, multifaceted upheaval. Even within the fossil record, we see hints of evolutionary last stands. Some species exhibit changes in bone structure, size, or population density that suggest attempts to cope with new environmental pressures. Perhaps they migrated, or adapted dietarily, or changed reproductive strategies. Yet these adaptations were not enough. In the face of planetary-scale catastrophes, evolution operates too slowly. The survivors were those with inherent flexibility, small size, or ecological versatility. The extinction of dinosaurs marks not only the end of an era but also the reshaping of life on Earth. As they disappeared, ecological niches opened, allowing mammals, birds, and other groups to diversify and flourish. Dinosaurs' dominance, built over millions of years of adaptive innovation, was abruptly halted by a convergence of extraterrestrial and terrestrial forces, climate instability, and cascading ecological collapse. Their demise was a lesson in vulnerability, even for the most powerful and seemingly unstoppable lineages. Modern science continues to refine these theories. High-resolution geological data, computer simulations, and new fossil discoveries provide an ever-clearer picture of the events surrounding the K-PG boundary. Paleontologists debate the relative importance of the asteroid versus volcanism, the timing of climate shifts, and the intricacies of ecosystem collapse. Yet all evidence points to a combination of forces. Earth's environment transforms so rapidly and so severely that even the most evolved and resilient dinosaurs could not endure. Through this lens, the extinction of dinosaurs is not a simple story of sudden catastrophe. It is a complex narrative of planetary change, ecological stress, and evolutionary pressure. It is a reminder that life, no matter how dominant, is vulnerable to forces beyond its control. And as we examine the layers of rock, the chemical signatures, and the fossilized remains, we gain insight not only into the end of the dinosaurs but also into the fragile balance that sustains life on Earth. The asteroid impact, with its immediate devastation, the relentless volcanism, reshaping climate and soil, the gradual yet profound climate shifts, and the resulting ecological collapse. These forces combine to erase the dinosaurs from the planet. Yet, within this ending lay the seeds of a new beginning, the survivors, the mammals, the birds, and the countless other lineages that would inherit the Earth. Even today, the scale of this extinction is staggering. Imagine creatures that once roamed continents, some reaching over 100 feet in length, suddenly gone from the world. Forests regrow without their massive herbivores. Predators vanished, leaving open niches. Oceans, rivers, and skies saw cascading changes in life forms. The Earth, resilient and adaptive, continued, but the age of dinosaurs, with all its diversity, drama, and majesty, was over. The Dino family tree, theropods, sauropods, ornithischians, and their fascinating connections, the story of life on Earth is written not just in individual species, but in the branches of the great tree of evolution. For dinosaurs, this tree is immense, sprawling across time, continents, and ecosystems, with roots deep in the Triassic and branches reaching toward the skies of the Cretaceous. Understanding the dinosaur family tree is like tracing the threads of a vast, interconnected web, where every species, no matter how small or mighty, plays a role in the story of survival, adaptation, and transformation. At the very base of this tree, the earliest dinosaurs split into two primary lineages, Saurischia, the lizard-hipped dinosaurs, and Ornithischia, the bird-hipped dinosaurs. These names, derived from the shape of their pelvic bones, reflect one of the most fundamental anatomical differences that shaped the evolutionary paths of countless species. Saurischians include both the fearsome theropods and the towering sauropods, while Ornithischians encompass a dazzling array of armored, horned, and hornless herbivores. Let's begin with theropods, the lizard-hipped predators. Theropods are perhaps the most famous of the dinosaur groups, not just for their size and ferocity, but for their evolutionary significance. From small, feathered hunters the size of modern turkeys to the colossal Tyrannosaurus rex, theropods display a remarkable range of adaptations. Their defining characteristics: hollow bones, sharp teeth, three-toed limbs, and powerful tails allowed them to be agile, efficient, and in many cases, apex predators of their ecosystems. But theropods are not just extinct hunters, they are the ancestors of all modern birds, a lineage that bridges the Mesozoic past with the present. Parallel to the rise of theropods were the sauropods, the gentle giants of the lizard-hipped lineage. These creatures took the other evolutionary path, moving away from predation and instead embracing gigantism and herbivory. From the long-necked Brachiosaurus to the whip-tailed Diplodocus, sauropods evolved enormous bodies to reach towering vegetation, with bones reinforced for weight-bearing and necks designed for both browsing and balance. Their evolution demonstrates a different kind of adaptation, one focused not on speed or cunning, but on scale, endurance, and efficiency. Even within this lineage, diversity flourished. Some species favored dense forests, others open plains, and some even coexisted with smaller predators that had evolved to hunt in herds or ambush strategies. While theropods and sauropods dominated the lizard-hipped side of the tree, ornithischians were forging their own path, a bird-hipped lineage that prioritized defense, diet, and ecological versatility. Ornithischians include stegosaurs, ankylosaurs, ceratopsians, hadrosaurs, and many more. Here, the family tree branches into fascinating adaptations: armor plating, tail clubs, horns, frills, and complex dental arrangements. Each adaptation represents a solution to environmental pressures, predation threats, and the struggle for survival. Ornithischians illustrate how evolution explores not just size or strength, but ingenuity, innovation, and even social behavior. Within the theropod branch, further subdivisions emerge. Early coelurosaurs were small, feathered hunters experimenting with speed, agility, and perhaps even primitive social interactions. Later, tyrannosaurids evolved massive skulls, bone-crushing jaws, and remarkable intelligence for predators of their size. Dromaeosaurids, the so-called raptors, evolved sickle-shaped claws and coordinated hunting strategies, showcasing parallel evolution of predatory efficiency in different ecosystems. The connections between these groups are not just anatomical, they reveal an evolutionary strategy, a blueprint of survival that spans millions of years. Sauropods, too, reveal fascinating connections. Diplodocids and brachiosaurids, while both massive, evolved in distinct ways, the former optimized for long, whip-like tails and horizontal necks, the latter for elevated browsing and pillar-like limbs. Within the sauropod lineage, the interplay between body size, neck length, limb structure, and feeding strategy demonstrates how small variations in anatomy could lead to vastly different ecological roles. Evolutionary innovation here was about maximizing efficiency, exploiting niches, and ensuring that even among giants, specialization could thrive. Ornithischians, with their diversity, present one of the richest chapters in the dinosaur family tree. Stegosaurs evolved plates that may have been used for thermoregulation or display, while ankylosaurs developed heavy armor and tail clubs for defense. Ceratopsians, including Triceratops, evolved frills and horns, creating species-specific identities that could signal dominance. Attract mates or ward off predators. Hadrosaurs, the duck-billed dinosaurs, developed intricate dental batteries to process tough vegetation efficiently, and some evidence suggests they communicated using resonating chambers in their skulls. The connections across these species, while sometimes separated by millions of years and thousands of miles, reveal an underlying theme. Evolution repeatedly experiments, adapts, and refines successful strategies. It is important to note that the dinosaur family tree is not just a collection of isolated branches, it is an intricate web of connections, convergences, and divergences. Parallel evolution appears repeatedly: armored plates in ankylosaurs and stegosaurs, long necks in separate sauropod lineages, predatory claws in different theropods. These convergences highlight the pressures of environment, predation, and competition, showing that evolution can arrive at similar solutions independently, even when lineages are far apart in the tree. Fossils reveal the anatomy of these connections. Skeletal similarities indicate common ancestry, while variations reveal adaptive divergence. Teeth show diet specialization. Limb bones indicate locomotion strategies, and cranial structures hint at sensory capabilities and social behaviors. These anatomical clues allow paleontologists to trace lineages, reconstruct family trees, and understand not only who these dinosaurs were, but how they were related and how evolution sculpted their diversity. The story of birds emerging from theropods is one of the most astonishing connections in this tree. Tiny, feathered coelurosaurs, experimenting with feathers perhaps initially for insulation or display, eventually developed powered flight. This lineage, once a small offshoot of theropods, survives today as birds, the living legacy of dinosaurs. It is a vivid demonstration of how the branches of the dinosaur family tree reach not just into the past, but into the present. Within the broader picture, the family tree also reveals ecological interactions. Theropods hunted herbivorous sauropods and ornithischians. Sauropods grazed forests and plains, shaping vegetation and influencing ecosystems. Ornithischians, with defensive adaptations, influenced predator behavior, social structures, and competition for resources. Each branch of the tree is not just a lineage, it is a thread in a dynamic ecosystem, connecting anatomy, behavior, and environment across millions of years. Even minor branches of the family tree tell important stories. Small omnivorous theropods experimented with diets, social behavior, and locomotion. Lesser-known ornithischians evolved specialized defenses or feeding strategies, often in isolated regions. These minor branches, while less famous, illustrate evolution's continuous experimentation. Some experiments failed, others succeeded, but each contributed to the diversity and resilience of the Mesozoic world. Geography and time also shaped these connections. Isolated continents produced unique lineages, while land bridges and shifting seas allowed dispersal and convergence. Asia, North America, South America, Africa, and Europe each hosted its own evolutionary experiments, yet similar forms often appeared in parallel, connected by environmental pressures and convergent strategies. The family tree is therefore both a map of ancestry and a mirror of ecological dynamics, showing how life responded to the planet's changing face. Behavioral evidence also reflects family tree connections. Herding in sauropods and ornithischians, coordinated hunting in theropods, nesting behaviors, parental care, all evolved within specific lineages, showing both inherited traits and independent innovation. The tree is alive not just with bones, but with behavior, interaction, and adaptation. The sheer diversity within the dinosaur family tree underscores evolution's creativity. From diminutive Compsognathus to colossal Argentinosaurus, from feathered Velociraptor to armored Ankylosaurus, from horned Triceratops to flat-headed Hadrosaurs, each branch tells a story of adaptation, survival, and connection. Even as continents drifted, climates shifted, and ecosystems changed, the branches of this tree remain dynamic, resilient, and fascinatingly interwoven. By studying these connections, scientists can reconstruct not only evolutionary history but also ecological relationships. The dinosaur family tree is a living record of experimentation, adaptation, and survival, illustrating how anatomy, behavior, and environment are deeply interconnected. It is a story written across time, continents, and species, a testament to life's ingenuity and persistence. Size, shape show-offs, from tiny Compsognathus to gigantic Argentinosaurus, evolution of extremes. The world of dinosaurs was a stage of extremes, a theater of life where size, shape, and spectacle were the ultimate tools of survival and display. From creatures barely larger than a modern chicken to giants that dwarfed buildings, evolution experimented boldly, crafting forms that were both functional and awe-inspiring. To understand this story is to witness the audacity of nature, the inventiveness of adaptation, and the astonishing diversity that unfolded over millions of years. Consider first the tiniest of the Mesozoic, Compsognathus. Barely 3 feet long, feathered, agile, and light as air, this small predator hunted insects, lizards, and perhaps smaller dinosaurs. Its diminutive size allowed it to navigate underbrush, slip into narrow crevices, and exploit niches inaccessible to larger predators. But size alone was not its only advantage. Its speed, keen eyesight, and perhaps even a degree of social cunning made it a survivor in a world where larger, more imposing creatures seemed to dominate. Compsognathus reminds us that in evolution, power is not measured merely by mass, but by adaptability, precision, and specialization. At the other end of the spectrum stood giants like Argentinosaurus, a sauropod that could stretch over 100 feet from head to tail. Its massive frame required bones the size of tree trunks, pillar-like legs to support unimaginable weight, and a heart capable of pumping blood to the farthest reaches of its enormous neck. Its sheer size was a defense mechanism. Predators dared not attack such colossal creatures lightly. Argentinosaurus and its fellow sauropods evolved not for speed or cunning, but for dominance through scale, reshaping ecosystems as they moved in herds across floodplains, munching on massive quantities of vegetation, and leaving footprints that would echo through the fossil record for millions of years. Between these extremes, the Mesozoic world teemed with creatures of every conceivable form and function. Theropods like Velociraptor were small, feathered, and fast, coordinating hunts with precision and intelligence. Tyrannosaurus rex, in contrast, combined enormous size with powerful jaws, demonstrating that evolution could produce apex predators capable of dominating entire continents. Among ornithischians, ceratopsians like Triceratops showcased defensive architecture, horns, frills, and muscular bodies, while stegosaurs displayed extravagant plates and spiked tails. Armor, frills, and spikes were not mere decoration, they were the result of millions of years of selective pressures, balancing protection, display, and thermoregulation. The evolution of size was not random. It was driven by ecological pressures, predation, food availability, and reproductive strategies. Herbivores could grow larger to reach higher foliage, store energy, or deter predators. Predators could grow larger to tackle bigger prey or refine their hunting techniques. Conversely, small size allowed for speed, stealth, and access to hidden resources. Across millions of years, evolution tested the limits, producing extremes in both directions and sometimes within the same lineages. Consider the interplay of shape and function. Long necks, whip-like tails, armored backs, sharp claws, and feathered appendages were all products of evolutionary experimentation. A Brachiosaurus stretched its neck high to access treetop leaves, while a Diplodocus extended its whip-like tail for defense or communication. Stegosaurus plates may have served dual functions: a display to attract mates and thermoregulation to balance body temperature. Every curve, every spike, every extension was a solution to a problem: feeding efficiency, predator defense, mating success, or environmental adaptation. Display and showmanship were also evolutionary strategies. Many dinosaurs evolved structures meant to impress, intimidate, or communicate. Frills, horns, crests, and colorful feathers were not mere aesthetics, they played vital roles in social interaction. A Triceratops frill could signal dominance or health to rivals. A theropod's feathers could convey status, attract mates, or confuse competitors. These display features intertwined with size and shape, illustrating that evolution values not just survival, but also communication and influence within populations. The extremes of size also influenced behavior and social structure. Massive sauropods likely traveled in herds, moving in coordinated groups for protection and reproductive success. Smaller predators may have hunted in packs or used stealth and agility to ambush prey. Size dictated not just the physical capabilities of dinosaurs, but also their roles within ecosystems, their interactions, and their strategies for survival. Large, imposing predators relied on strength and intimidation, while smaller species relied on cunning, cooperation, or niche specialization. Parallel evolution further amplified these extremes. Across different continents, unrelated species developed similar strategies independently. Long-necked herbivores, heavily armored herbivores, small nimble predators, and towering carnivores appeared repeatedly in separate ecosystems. Evolution tested solutions in multiple arenas simultaneously, resulting in astonishingly similar adaptations in creatures that were millions of years and thousands of miles apart. Environmental pressures shaped these adaptations profoundly. Food sources dictated herbivore size, predation pressure dictated defense and hunting strategies, and climate influenced growth, metabolism, and behavior. Seasonal droughts, shifting rivers, volcanic eruptions, and tectonic activity created dynamic landscapes, forcing dinosaurs to evolve flexibility or face extinction. Every extreme form, every bizarre adaptation, was an answer to these environmental challenges, a testament to evolution's relentless creativity. Even within a single lineage, size extremes were remarkable. Early theropods were small and feathered. Later descendants evolved into monsters like Spinosaurus and Tyrannosaurus. Sauropodomorphs began modestly and evolved into Argentinosaurus-sized titans. Ornithischians showed similar patterns, evolving elaborate ornamentation and sometimes enormous body sizes, or maintaining smaller, agile forms to navigate specific niches. Evolution explored every possibility, from miniature efficiency to colossal dominance, without prejudice, without haste, and always under the watchful hand of natural selection. Fossils reveal not only bones but the implications of size and shape. Limb proportions suggest locomotion speed, muscle attachment sites indicate strength, and skull and dental structures reveal dietary specialization. Even small adjustments in anatomy could create entirely new ecological opportunities. A slightly longer neck could access previously unreachable foliage. A slightly larger claw could expand hunting potential. A change in tail shape could alter defense strategies or social signaling. Evolution was meticulous, experimental, and astonishingly effective. In the visual landscape of the Mesozoic, size and shape also communicated identity. Herds of massive sauropods moving through floodplains, packs of theropods coordinating hunts, and groups of armored ornithischians defending territory presented a spectacle of form and function. Evolution not only created tools for survival but choreographed a dance of display and intimidation, where the size and shape of a dinosaur were as much a statement as a functional adaptation. And yet, extremes carried costs. Large size required enormous food intake, precise skeletal support, and complex physiology. Small size, while offering agility and stealth, demanded speed, intelligence, and adaptability to avoid predation. Every adaptation was a trade-off, every form a compromise. Evolution, in sculpting these extremes, was constantly balancing opportunity and risk, creating creatures that were remarkable not just for their survival, but for the elegance and audacity of their adaptations. Through this lens, the dinosaur's world appears as a spectrum of possibility, where size and shape were tools of survival, adaptation, and communication. From the tiniest Compsognathus to the monumental Argentinosaurus, from feathered hunters to armored herbivores, evolution explored extremes tirelessly, producing a diversity that continues to awe us millions of years later. The story of size, shape, and showmanship is not merely about bones, it is about ingenuity, strategy, and the relentless drive of life to fill every niche, conquer every challenge, and express itself in the most extraordinary ways. Anatomy and physiology, skeletons, muscles, feathers, and the mechanics of movement. Beneath the towering forms, the spikes, the claws, and the feathers, lies the machinery of life itself, the anatomy and physiology of dinosaurs. To understand how these magnificent creatures moved, hunted, and survived is to peer into the very mechanics that powered the Mesozoic world. Every bone, muscle, feather, and sinew was a testament to millions of years of evolutionary refinement, each component designed not just for survival, but for extraordinary performance. At the foundation of all movement was the skeleton. Unlike the rigid frames of many modern animals, dinosaur bones were marvels of engineering. Theropods, for instance, possessed hollow bones, lightweight yet strong, allowing for agility without sacrificing structural integrity. This combination of strength and minimal weight made rapid movement possible, whether stalking prey, leaping over obstacles, or maintaining balance at high speeds. The hollow structures also may have supported air sacs connected to the lungs, hinting at an advanced respiratory system that helped sustain high activity levels. Sauropods, in contrast, required skeletons designed for sheer size and weight. Vertebrae were reinforced with internal struts, creating a lattice-like structure that could bear immense loads without collapsing. Limbs function like pillars, columnar and straight, supporting bodies that could weigh tens of tons. Even the long necks, seemingly precarious, were marvels of biomechanical design. A combination of vertebral structure, ligaments, and musculature allowed these giants to reach treetops, graze widely, and maintain balance as they moved across vast floodplains. The skeletons of sauropods were simultaneously flexible and immovable where it mattered, optimized for both feeding and locomotion. Musculature further enhanced the capabilities of dinosaurs. Powerful limb muscles allowed theropods to sprint, leap, and strike with precision. In predators, forelimbs might have been adapted for grasping, tearing, or balance, depending on the species. Muscles in the tail worked as counterbalances, stabilizing movement and aiding in turning, hunting, or display. Sauropods, despite their bulk, relied on massive muscle groups to control neck position, propel massive legs, and maintain posture. Muscles were not just for movement, they were integrated into an entire system of balance, respiration, and coordination. Feathers and integumentary structures were another layer of complexity. Initially evolving perhaps for insulation or display, feathers influenced thermoregulation, aerodynamics, and social signaling. In small theropods, feathers could have assisted in gliding, balance, or precision strikes, giving them a subtle advantage in hunting and evasion. In larger species, display feathers may have conveyed information about status, health, or readiness to mate. The interplay between feathers and musculature illustrates the sophisticated integration of anatomy and physiology, where movement, communication, and survival coalesced into a single system. The mechanics of movement were equally intricate. Bipedal dinosaurs, for instance, required precise alignment of spine, pelvis, and limbs to maintain stability. A forward-leaning theropod balanced its torso with a heavy tail, muscles along the back and legs coordinating to achieve speed without collapse. Quadrupedal dinosaurs, like sauropods and many ornithischians, distributed weight through sturdy limbs, reinforced joints, and interlocking vertebrae. Even subtle changes in gait, posture, or limb placement could have profound effects on energy efficiency, speed, and endurance. Specialized adaptations highlight evolution's ingenuity. Ankylosaurs, heavily armored and low-slung, moved with a surprising degree of agility despite their armor. Their limb muscles, pelvic structures, and spinal arrangements allowed them to shift weight, brace for attacks, and maneuver in complex terrain. Ornithopods, like hadrosaurs, combined strong hind limbs with flexible forelimbs to graze, navigate wetlands, and even swim when necessary. Every adaptation in anatomy was intertwined with physiology, enabling a wide range of behaviors from predator evasion to complex social interaction. The evolution of sensory anatomy further influenced physiology. Eyes placed for binocular vision enhanced depth perception, critical for hunting, foraging, and navigation. Inner ear structure suggested balance adaptations for both speed and agility. Muscles controlling jaws and necks reflected dietary specialization, powerful bites for carnivores, grinding precision for herbivores. Even subtle anatomical features, like nasal passages, could indicate adaptations for thermoregulation or enhanced olfaction. Anatomy was not static, it evolved in tandem with behavior and environment, creating an integrated system capable of remarkable feats. Consider tail anatomy. In many theropods, tails acted as dynamic counterbalances, stabilizing the body during rapid movement. In stegosaurs and ankylosaurs, tails transformed into defensive weapons, the musculature and skeletal design precisely tuned to strike, swing, or brace. Sauropod tails, often massive, served multiple purposes: balance, display, and potentially even as a whip for defense. Each tail, whether delicate or formidable, exemplifies how anatomy and physiology were interdependent, blending survival, utility, and sometimes even spectacle. Even respiratory and cardiovascular physiology must be considered. Hollow bones, large lung capacities, and potential air sac systems allowed many dinosaurs to sustain high metabolic activity. Theropods, with active hunting strategies, would have required efficient oxygen delivery to muscles for bursts of speed and stamina. Sauropods, with massive bodies, relied on cardiovascular adaptations to pump blood through enormous necks and maintain oxygenation across tens of meters of tissue. Evolution solved these physiological challenges with elegant efficiency, balancing size, energy, and endurance in ways still studied and marveled at today. The integration of anatomy and physiology is perhaps most apparent in locomotion. Theropods relied on coordinated limb, tail, and spine movement to sprint with precision, sometimes over uneven terrain. Sauropods moved ponderously but with surprising grace, using energy-efficient gaits to traverse hundreds of kilometers in search of food. Ornithischians displayed both bipedal and quadrupedal locomotion, adapting posture and gait to environmental demands. Even minor shifts in anatomy, such as elongated limb bones or modified joints, had cascading effects on how these dinosaurs moved, fed, and interacted. Predation, defense, and display all fed back into anatomy. Armor evolved in ankylosaurs and stegosaurs, influencing musculature and mobility. Predators evolved claws, powerful jaws, and flexible limbs for hunting efficiency. Crests, frills, and display structures required muscular and skeletal support to function without hindering survival. Evolution was not concerned with aesthetics for humans. Every form, every structure, every sinew was honed for survival, adaptation, and communication. Even growth and development reveal fascinating insights. Juvenile dinosaurs often differed significantly in anatomy from adults, reflecting changes in physiology, diet, and mobility. Some species grew rapidly, developing defensive structures or size-based advantages over predators. Muscles and bones matured in coordination, optimizing efficiency at every life stage. Feathers and integumentary structures may have appeared first in juveniles for insulation, later contributing to display or aerodynamic function. Growth itself was an active component of physiology, integrated with survival strategies. The fossil record preserves these marvels. Skeletal reconstructions, muscle attachment sites, and impressions of skin or feathers allow us to infer how dinosaurs moved, hunted, and lived. Detailed study of joint structure reveals flexibility and range of motion. Bone microstructure offers clues about growth rate, metabolism, and endurance. Even tiny details, like claw curvature or vertebral articulation, unlock stories of how these creatures navigated their world. In essence, the anatomy and physiology of dinosaurs represent a symphony of design, each component interacting with the next, creating creatures capable of astonishing movement, endurance, and adaptability. Skeletons supported massive or agile frames. Muscles provided strength, speed, and precision. Feathers and integument aided thermoregulation, display, and sometimes even flight. The mechanics of movement were refined to perfection over millions of years, resulting in a diversity of form and function unparalleled in the animal kingdom. Behavior, habits, daily life, hunting, foraging, migration, nesting, and survival strategies. Imagine walking through a Mesozoic forest, the air thick with the smell of vegetation and the distant cries of creatures both large and small. The world of dinosaurs was not static, it pulsed with life, activity, and complex behavior. Every day was a negotiation with the environment, a delicate balance between hunting and evading, foraging and conserving, migrating and nesting. Their survival depended not just on anatomy and physiology, but on behaviors honed through millions of years of adaptation. Predatory behavior was perhaps the most striking aspect of dinosaur life. Theropods, the carnivorous hunters, demonstrated remarkable intelligence, coordination, and strategy. Some species hunted alone, relying on stealth, speed, and ambush. Others may have hunted in packs, coordinating movements to corner or exhaust prey. The fossil record and trackways hint at complex group behavior, suggesting that social coordination was a vital component of their daily life. Muscles, senses, and skeletal mechanics all worked in harmony, enabling hunters to strike with precision, whether at dawn in a misty forest or across open plains under the harsh sun. Herbivorous dinosaurs also displayed intricate foraging behavior. Feeding strategies varied dramatically depending on size, dentition, and anatomy. Hadrosaurs, the duck-billed dinosaurs, employed intricate dental batteries to grind tough plant material efficiently, while ceratopsians used their beaks and horns to strip vegetation. Sauropods, with their colossal necks, accessed treetops, while stegosaurs grazed closer to the ground. Migration may have played a role for many species, following seasonal shifts in vegetation or moving to avoid droughts or predation pressures. Herd dynamics allowed for protection, with adults forming barriers around young or vulnerable members. Nesting and reproductive behavior reveal another layer of complexity. Fossilized nests and eggs provide a window into social and reproductive strategies. Many species return to specific nesting grounds, often in colonies, suggesting communal behavior and possibly cooperative protection of eggs. Some theropods may have incubated eggs, using body heat to regulate temperature, while others relied on environmental factors like sunlight or decomposing vegetation. Evidence of hatchling development and growth indicates that parental care varied among species, with some exhibiting prolonged nurturing while others relied on independence from birth. Migration was a critical component of daily life for many dinosaurs, especially herbivores dependent on seasonal vegetation. Fossilized trackways indicate that sauropods moved in massive herds across floodplains, leaving impressions that stretch for kilometers. These migrations were not random, they followed predictable patterns, allowing species to exploit rich feeding grounds while avoiding harsh climates. Migration required navigation skills, memory, and perhaps social learning, as younger members followed the experienced adults. Predators would have adapted their behavior accordingly, trailing herds or intercepting stragglers. Survival strategies extended beyond feeding and reproduction. Dinosaurs employed defensive behaviors to evade predators or protect their territories. Ornithischians like ankylosaurs and stegosaurs used tail clubs and spikes, while ceratopsians displayed intimidating horns and frills. Camouflage, herd formation, and vigilance were behavioral adaptations that increased survival odds. Predators, conversely, developed ambush tactics, cooperative hunting strategies, and acute sensory awareness to exploit weaknesses in prey behavior. The interplay of predator and prey created a dynamic system, constantly shaping and reshaping behaviors through evolutionary pressure. Daily life also involved social interaction. Evidence from fossilized trackways, nesting sites, and bone beds suggests that some species lived in groups, coordinated movements, and possibly communicated with one another. Vocalizations, display feathers, and posturing may have been used to establish dominance, attract mates, or signal danger. Herd dynamics, whether in massive sauropods or smaller ornithopods, required constant negotiation: who leads, who defends, and how to coordinate movement in complex landscapes. Social behavior was not just incidental, it was a survival strategy, a means to thrive in a competitive and dangerous world. Dinosaurs also displayed adaptability in response to environmental pressures. Seasonal changes, climatic shifts, volcanic activity, and other ecological stresses required flexible strategies. Some species altered diets, switching between plant types or scavenging opportunities. Others adjusted migration patterns, nesting timing, or social behavior to cope with changing conditions. Adaptability was crucial. Dinosaurs that could not modify behavior in response to environmental challenges were at higher risk of extinction. Even minor behavioral details mattered. Feeding posture, resting positions, grooming, and thermoregulation all contributed to survival. Theropods may have used sun and shade to regulate body temperature, while large herbivores like sauropods relied on herd movement and shade-seeking behavior. These small but vital actions reflect an intimate relationship with the environment, where behavior was the interface between physiology and survival. Fossilized evidence, trackways, nests, and coprolites, fossilized droppings, all offer glimpses into these behaviors. Trackways reveal movement patterns, group coordination, and even interactions between predators and prey. Nests show the care and strategies employed in reproduction. Coprolites provide dietary insights, revealing what species ate and how they processed food. Together, these data allow paleontologists to reconstruct not just anatomy, but the rhythm and choreography of daily life in the Mesozoic world. In essence, behavior, habits, and daily life were the true engines of survival for dinosaurs. Hunting strategies, foraging efficiency, migration patterns, nesting behaviors, social dynamics, and adaptability to environmental stress formed an intricate web that sustained life for millions of years. Each day was a combination of instinct, learned behavior, and ecological negotiation, finely tuned over millennia to maximize survival and reproductive success. The story of daily life in the age of dinosaurs is not static, it is dynamic, evolving, and deeply intertwined with environment, physiology, and social interaction. Every step, every hunt, every migration, and every nest tells a story of life and motion, a story of persistence, adaptation, and the remarkable ingenuity of creatures that dominated Earth long before humans arrived. Communication noise, roars, calls, posturing, and what fossils tell us about social behavior in the dense forests, sprawling plains, and floodplains of the Mesozoic, life was not silent. The world of dinosaurs was filled with subtle sounds, dramatic displays, and complex communication, even if most of it is lost to time. Roars, calls, postures, and gestures formed a language, an unspoken system that conveyed danger, attraction, dominance, and cooperation. Though we cannot hear these voices directly, the fossils, trackways, and anatomical structures left behind offer extraordinary clues, allowing us to reconstruct the hidden symphony of their lives. Roars, deep and resonant, may have echoed across valleys, serving multiple functions. Large theropods, with robust skulls and resonating chambers, could have produced calls that warned rivals, challenged intruders, or coordinated hunts. These sounds were more than intimidation, they communicated social status, territory boundaries, and perhaps even emotional states. In some species, particularly the larger predators, vocalizations may have been critical in establishing dominance hierarchies within a group, ensuring order and survival. Calls, on the other hand, were often subtle, nuanced, and highly specific. Smaller theropods, ornithopods, and possibly even ceratopsians may have employed chirps, whistles, or clicks to maintain contact with conspecifics. These calls could convey location, alert companions to predators, or coordinate group activities. Fossilized evidence, such as the structure of the inner ear and the hyoid bone, supporting vocal structures, indicates that dinosaurs had the anatomy to produce a range of sounds, suggesting that communication was vital for daily life. Posturing was another critical layer of communication. Visual displays, feathered crests, frills, and body orientation conveyed messages without sound. Triceratops, for example, may have used horn and frill positions to display aggression or readiness to mate. Feathered theropods could have fanned colorful plumes to assert dominance or attract attention. Even tail movements, body arching, or head positioning could communicate complex social signals, particularly in dense forests or across long distances. Fossilized crests, quills, and frills are silent today, yet they reveal that appearance and posture were integral to interaction. Group behavior amplifies the importance of communication. Herding species, like sauropods or hadrosaurs, relied on signals to coordinate movement. Vocalizations could alert others to predators, indicate resource locations, or maintain cohesion in large migratory groups. Social coordination required more than instinct, it required the evolution of communication systems. Fossil trackways showing parallel movement of multiple individuals suggest that signals, audible, visual, or tactile, enabled organized migration and daily routines. Courtship and mating behavior added another layer to communication. Bright crests, frills, and ornamental feathers were likely used in elaborate displays, attracting mates or deterring rivals. Specific postures, synchronized movements, or ritualized calls may have formed complex mating dances. Fossil evidence indicates sexual dimorphism in many species, suggesting that visual and auditory communication played a central role in reproduction and social selection. Evolution leveraged sound and sight to reinforce survival, status, and genetic continuity. Predator-prey communication also shaped behavior. Herbivores could warn each other of predators through calls, display, or sudden movements. Small vocalizations, tail flicks, or body postures may have transmitted information quickly across a herd, increasing survival chances. Conversely, predators needed stealth, subtlety, and precision in their own communication, whether signaling pack coordination or confusing prey. The interplay between predator and prey created a rich tapestry of communicative strategies, continuously evolving under selective pressure. Fossils reveal more than structure, they hint at behavioral sophistication. The discovery of resonating chambers in some skulls suggests that sound production was not accidental but specialized. Variation in crest size, frill shape, and feather arrangement between individuals implies visual signaling was nuanced, perhaps even allowing recognition of individuals within groups. Bone beds, showing many individuals of a species together, indicate that social structure was reinforced by communication, enabling cooperative defense, hunting, and reproduction. Even subtle anatomical features, like the shape of the beak or the curvature of claws, might have been part of communication. Display structures sometimes served multiple purposes: thermoregulation, defense, and signaling simultaneously. The complexity of these adaptations shows that communication was a driving force in evolution, shaping not only behavior but morphology, physiology, and ecology. Interestingly, communication may have included tactile interactions. Nuzzling, gentle nudges, or physical posturing could reinforce bonds between parents and offspring or among social groups. Nesting behavior, indicated by fossilized eggs and juvenile remains, suggests that tactile and auditory signals coordinated care, protection, and feeding. Parental care likely depended on a sophisticated blend of signals, ensuring that young could survive in a dangerous and unpredictable world. In essence, the world of dinosaur communication was a multisensory landscape. Sound, sight, posture, and touch intertwined to convey meaning, coordinate behavior, and sustain social structure. Evolution engineered creatures that were not only physically impressive but socially intricate, with communication systems enabling survival, cooperation, and reproduction across millions of years. Dinosaurs, then, were not solitary, silent behemoths. They were social actors, performers in a grand drama, utilizing every available channel to convey information, assert status, and maintain cohesion. Roars that shook the valleys, subtle chirps across the underbrush, fan feathers flashing in the sun, all were part of an unseen language, encoded in anatomy, behavior, and environment. Fossils may be silent, but they speak volumes about the complexity of communication in the Mesozoic. Every display, every call, every gesture carried meaning, and together, these signals created the rhythm of daily life. From the smallest coelurosaur to the largest sauropod, communication was not incidental, it was essential. It shaped hunting strategies, herd behavior, mating rituals, and survival tactics. The more we studied the fossil record, the more we realized that the dinosaurs' world was alive with information, a continuous symphony of noise, gesture, and intention, orchestrated over millions of years. Love, eggs, reproductive biology, courtship rituals, nesting grounds, egg-laying, and parental care, in the heart of the Mesozoic, amidst towering ferns and shifting rivers. Life found its most intimate expression in love, reproduction, and the continuation of species. Dinosaurs, often imagined as colossal, terrifying beasts, also engaged in behaviors of delicate care, elaborate courtship, and nurturing that rival even the most intricate human rituals. Their reproductive biology was a world of strategy, innovation, and devotion, encoded in anatomy, behavior, and environment. Courtship was the first act in this drama of life. Visual displays were central. Crests, frills, and colorful feathers broadcasted health, strength, and genetic fitness to potential mates. In some theropods, feathered plumes could be fanned in intricate patterns, creating displays both spectacular and meaningful. Horns on ceratopsians, frills on stegosaurs, and even the size of claws or tail structures could signal dominance or readiness. Such displays were not static, they evolved over millions of years, refined by the pressures of selection to convey information quickly and effectively to an audience of discerning mates. Auditory signals complemented visual displays. Low-frequency roars, resonant calls, or subtle chirps communicated presence, attraction, or readiness to reproduce. Fossil evidence of specialized cranial structures suggests that sound was a carefully controlled tool. Modulated for distance, intensity, and meaning. Together with physical displays, these signals formed an intricate language of courtship, invisible to us but essential for the survival of species. Nesting grounds were central to reproductive success. Many species returned year after year to the same locations, often forming colonies where multiple individuals laid eggs in close proximity. Fossilized nests reveal careful construction. Impressions of vegetation, mud, and soil suggest dinosaurs selected sites for drainage, temperature regulation, and predator avoidance. Such choices reflect an awareness of environment, strategic planning, and a drive to maximize offspring survival. Egg-laying was not merely functional but a carefully managed process. Egg size, shape, and number varied across species, reflecting life strategy, body size, and environmental constraints. Smaller theropods produced clutches of dozens of eggs, relying on quantity to ensure survival. Larger sauropods laid fewer, more robust eggs, investing in the potential success of each hatchling. Shell structure, texture, and porosity were designed to regulate gas exchange, temperature, and humidity. Biological engineering that allowed embryos to develop safely over weeks or months. Parental care in dinosaurs was more sophisticated than often imagined. Evidence suggests that some theropods and ornithischians brooded their nests, using body heat or strategically arranged eggs to maintain optimal temperatures. Fossilized juvenile tracks near adult footprints hint at protection, guidance, and shared feeding behavior. Nesting behavior, combined with vigilance, ensured that young had a higher chance of survival in a world filled with predators, environmental hazards, and competition. Social dynamics influenced reproductive behavior. In some species, communal nesting may have allowed individuals to share the burden of defense, while in others, dominant males or females may have monopolized access to prime nesting sites. Territorial disputes, rival courtship displays, and hierarchical interactions were likely intertwined with reproductive strategy, ensuring that the strongest, most adapted individuals passed on their genes. Communication, both visual and auditory, played a critical role in these interactions. Growth and development of the young were also intricately tied to reproductive strategy. Hatchlings often differed from adults in behavior, size, and anatomy, reflecting ecological pressures and survival needs. Rapid growth, protected by vigilant parents or herd members, allowed juveniles to reach sizes where predation risk diminished. Feathers, initially perhaps for insulation, aided survival, and later contributed to display or flight. Each stage of life was carefully orchestrated by evolution, balancing vulnerability with adaptability. Migration and environmental selection also intersected with reproductive cycles. Some species may have traveled long distances to reach optimal nesting grounds, timing egg-laying with seasons of abundant vegetation, water availability, or predator scarcity. Herd movement and synchronization of reproductive timing ensured that offspring were born into environments most conducive to survival. The fossil record of trackways, nesting sites, and bone beds provides compelling evidence of these dynamic strategies. Even the act of raising young likely involved behavioral sophistication. Food provision, protection against threats, and teaching survival skills may have been part of daily life for some species. Fossilized nests containing multiple age groups suggest that juveniles may have remained in proximity to adults for extended periods, learning critical behaviors essential for hunting, foraging, and social interaction. These extended interactions reveal an emotional and functional investment in progeny, highlighting that love, in the broadest evolutionary sense, was central to survival. In essence, dinosaurs' reproductive biology was a tapestry woven from courtship, nest construction, egg-laying, parental care, and environmental strategy. Every behavior, anatomical adaptation, and physiological mechanism was honed to ensure the continuation of the species. They were not simply instinct-driven automatons, they were strategists, engineers, and nurturers shaping the next generation in an ever-changing and often perilous world. From the first display of a feathered crest to the final hatchling leaving the nest, the story of love, eggs, and reproduction in Dinosaurs is a story of life at its most fundamental and awe-inspiring level. Evolution crafted behaviors and structures that allowed species to thrive, adapt, and persist for millions of years, leaving a legacy that continues to fascinate us today. Predators and prey dynamics, top predators, prey adaptations, and the ultimate arms race. In the vast landscapes of the Mesozoic, an intricate, relentless drama unfolded every day, the eternal struggle between predator and prey. It was a world of tension, anticipation, and strategic brilliance, where survival depended not just on strength, but on cunning, adaptation, and timing. From the towering tyrannosaurs to the fleet-footed ornithopods, evolution staged an arms race that would last millions of years, sculpting every tooth, claw, and instinct with unyielding precision. Top predators were the ultimate exemplars of evolutionary engineering. Tyrannosaurus rex, with its massive skull, serrated teeth, and powerful jaw, could crush bone effortlessly, transforming entire ecosystems simply by its presence. But raw power alone was never enough. Apex predators relied on keen senses, eyesight tuned to track movement across vast distances, olfactory capabilities to detect prey from afar, and hearing sensitive enough to detect the faintest rustle in a dense forest. Every muscle, ligament, and bone was tuned for efficiency, enabling bursts of speed, swift pivots, and lethal strikes. Their daily life revolved around locating, stalking, and overpowering prey, a constant exercise in precision and patience. Meanwhile, prey species were far from passive. Ornithopods, ceratopsians, and sauropods developed an array of adaptations to avoid becoming dinner. Herding behavior provided safety in numbers, coordinated movement and collective vigilance allowed groups to detect predators early, respond swiftly, and even confuse attackers. Defensive structures, horns, spikes, armored plating, and tail clubs, were not mere ornaments, they were weapons honed through millennia of predator-prey interaction. Each encounter left an imprint on evolution, shaping the anatomy, behavior, and survival strategies of both predator and prey. The arms race extended beyond the obvious. Speed, agility, and endurance became vital. Smaller theropods honed hunting strategies that leveraged ambush, stealth, and pack coordination. Herbivores evolved rapid flight responses, zigzagging escape patterns, and astonishing bursts of speed to evade capture. In larger herbivores, sheer size provided a buffer. An adult sauropod could outmatch most predators simply through mass. But juveniles remained vulnerable, protected only by herd strategy, camouflage, or parental vigilance. Evolution produced a spectrum of solutions, from raw strength to subtle cunning, from armor to agility. Communication played a critical role in this deadly game. Herding prey used vocalizations, tail movements, and visual cues to coordinate defense and warn others of approaching danger. Predators may have employed subtle signals to coordinate group hunts or to intimidate rivals. Fossil evidence of injuries and healed bones tells a story of countless encounters, near escapes, and adaptations that arose in response to each challenge. Survival was an ever-shifting calculus, where even the slightest advantage could determine life or death. Predators evolved in parallel with prey in a cycle of constant feedback. When prey developed faster running speeds or new defensive structures, predators adapted new hunting techniques, claws, teeth, or strategies. Stegosaurus' spiked tail may have arisen as a direct response to predatory threats, while tyrannosaurs refined their bite force and jaw mechanics in response to increasingly robust herbivores. Evolution was both inventive and relentless, testing every adaptation across millions of years. Behavioral strategies were just as critical as anatomy. Some predators preferred ambush tactics, lying in wait near waterholes, nesting grounds, or migration routes. Others pursued endurance hunting, exhausting prey over long distances. Prey species responded with vigilance, synchronized movement, and sometimes even deception, hiding, feigning weakness, or retreating strategically. Every encounter, every chase, every failed attack was part of an ongoing dialogue between species, written in muscle, bone, and instinct. The environment amplified these dynamics. Dense forests, open plains, river deltas, and volcanic landscapes all shaped strategies. Stealth, camouflage, and knowledge of terrain became invaluable for both predator and prey. Seasonal changes forced migrations, altering hunting grounds and food availability. Water, vegetation, and shelter dictated movement, positioning, and survival strategies, creating a world where every behavioral decision had profound consequences. Even social structure influenced the arms race. Pack hunters may have coordinated attacks to overwhelm larger prey, while herd defense strategies relied on leadership, positioning, and collective movement. Juveniles learned through observation, adults honed tactics through experience, and every generation refined the strategies that had proven successful. Fossilized trackways show parallel movement, group coordination, and predator-prey encounters frozen in time, revealing an extraordinary behavioral sophistication. The ultimate expression of this arms race was adaptability. Both predators and prey had to innovate continually or risk extinction. A predator that specialized too narrowly could find its food scarce. A prey species that relied solely on size might fall to cunning ambush predators. The balance was delicate and unforgiving, pushing both sides toward evolutionary extremes: massive size, lethal weaponry, agility, speed, intelligence, and intricate social behaviors. In essence, predator-prey dynamics were the invisible hand shaping ecosystems. Every bite, chase, defense, and escape contributed to the evolutionary story of the Mesozoic. Survival was never guaranteed, it demanded strategy, coordination, and constant adaptation. The arms race left a legacy written in bone, in fossilized footprints, in healed injuries, and in the astonishing diversity of life that thrived against the relentless pressure of predation. Through millions of years, this dance of life and death drove innovation, specialization, and complexity. Predators sculpted prey, prey sculpted predators, and together they created a dynamic, interdependent, and endlessly fascinating world. The fossil record captures fragments of these encounters, allowing us to glimpse the intensity, ingenuity, and relentless pace of life in the age of dinosaurs, a story of survival that resonates with the drama of evolution itself. Research discoveries, fossil digs. Famous paleontologists, and breakthrough discoveries. Beneath the sun-baked plains, hidden cliffs, and desert expanses lie the silent remnants of a world long gone. Fossils, buried for millions of years, are the whispers of the Mesozoic, waiting for curious hands and keen eyes to uncover their secrets. The history of dinosaur research is itself a journey, a tale of obsession, discovery, and wonder, shaped by scientists who devoted their lives to unearthing fragments of bones, teeth, and imprints that would forever change our understanding of life on Earth. Fossil digs are more than simple excavations, they are meticulous journeys into the past. Paleontologists approach the Earth with a blend of patience, precision, and anticipation, knowing that even the smallest fragment can reveal profound truths. The tools are humble: brushes, chisels, and plaster, but the stakes are immense. Each layer of sediment, each fragment of bone, must be interpreted with care, piecing together the architecture of life that existed millions of years ago. Fossils are fragile, yet they hold stories of entire ecosystems, predator-prey interactions, and evolutionary innovation. From the earliest discoveries in the 19th century to modern digs spanning continents, the story of paleontology is a tale of human curiosity and relentless pursuit. Early fossil hunters in Europe and North America often worked under harsh conditions, battling heat, cold, and isolation. They dug in deserts, riverbeds, and rocky outcrops, guided by intuition, luck, and sometimes pure obsession. Each find, whether a single tooth or a massive skeleton, challenged preconceptions about the past, fueling debates and inspiring generations of researchers. Famous paleontologists left indelible marks on the field. Names like Othniel Charles Marsh and Edward Drinker Cope evoke images of rivalry, ambition, and extraordinary discovery during the Bone Wars, a period of intense fossil competition in the late 1800s. Their discoveries, from the giant Allosaurus to the immense Brontosaurus, expanded knowledge and sparked fascination worldwide. These pioneers faced logistical nightmares, harsh landscapes, and scientific skepticism, yet their perseverance laid the foundation for modern paleontology. Across the globe, other figures contributed to our understanding. Barnum Brown, the discoverer of the first Tyrannosaurus rex specimen, braved remote and desolate locations, leaving behind one of the most iconic fossils in history. Roy Chapman Andrews, leading expeditions through the Gobi Desert, uncovered dinosaur eggs and entire skeletons that challenged assumptions about reproduction and behavior. These explorers combined adventure with science, turning paleontology into both a rigorous discipline and an odyssey of discovery. Modern paleontology has refined techniques, integrating technology and interdisciplinary methods to unlock secrets hidden in stone. CT scans reveal internal structures without damaging fossils. Isotopic analysis deciphers diet, migration, and climate interactions. Trackways, coprolites, and even fossilized skin or feathers add layers of detail previously unimaginable. Every dig, every lab analysis, every careful measurement contributes to a growing understanding of dinosaur biology, ecology, and evolution. Breakthrough discoveries have often rewritten the story of life itself. The revelation that some dinosaurs bore feathers challenged decades of assumptions, linking birds and theropods in ways that reshaped evolutionary biology. Fossilized embryos and nesting sites illuminated reproductive strategies, while trackways revealed complex social behavior and group dynamics. Each discovery is a puzzle piece, fitting into a broader picture of ecosystems, adaptation, and survival. Global collaboration has expanded our horizons. Paleontologists now work in deserts of Mongolia, riverbeds of Patagonia, and frozen landscapes of Antarctica. Fossil discoveries in Africa, Asia, and Europe highlight the diversity of dinosaur life across continents and climates. Collaborative research, data sharing, and international expeditions ensure that knowledge is cumulative, building upon the work of past generations while embracing new technologies and methodologies. Fossil digs are also exercises in patience and precision. The process of excavation often takes months or years. Bones may be encased in hard rock, requiring careful chiseling and stabilization with plaster jackets. Transporting specimens across rugged terrain demands ingenuity and endurance. Back in the lab, reconstruction begins, aligning bones, estimating missing parts, and using comparative anatomy to fill gaps. Every step is methodical, meticulous, and guided by scientific rigor, revealing the story hidden within mineralized remains. The interpretation of fossils is as crucial as their discovery. Each bone tells multiple stories: the age of the individual, its growth patterns, injuries sustained, and even signs of disease. Teeth can indicate diet, claw curvature reveals predatory strategies, limb proportions hint at locomotion and speed. By combining anatomical data with geological and environmental evidence, scientists reconstruct entire ecosystems, flourishing forests, predator-prey dynamics, and migratory patterns across continents. Paleontology is not static, it is a constantly evolving discipline. New discoveries often overturn long-held assumptions. The classification of species, the reconstruction of appearance and behavior, and our understanding of evolutionary relationships are continually refined. Even the smallest fossil fragment can trigger debates and inspire re-examination of previously accepted theories, highlighting the dynamic and self-correcting nature of science. Public fascination plays a role too. Museums, documentaries, and exhibitions translate fossil research into immersive experiences, bringing the ancient world to life. Iconic skeletons of T. Rex, Triceratops, and Brachiosaurus inspire awe, curiosity, and wonder, bridging the gap between scientific research and public imagination. Paleontologists not only uncover fossils but also tell stories, allowing us to witness life from millions of years ago, connecting the past with the present. The human stories behind these discoveries are equally compelling. Fieldwork often involves isolation, hardship, and risk. Researchers contend with extreme weather, remote locations, and logistical challenges, yet their dedication transforms dirt, rock, and bone into knowledge that shapes our understanding of evolution. The thrill of unearthing a perfectly preserved skeleton or the first fossilized egg is matched only by the intellectual satisfaction of piecing together a life from fragments, imagining how creatures lived, moved, and thrived. Innovation drives discovery. Advanced imaging, chemical analysis, and even artificial intelligence now assist in identifying subtle features invisible to the naked eye. Fossilized soft tissues, skin impressions, and even traces of proteins or DNA offer unprecedented insight into physiology, behavior, and evolutionary relationships. Technology allows paleontologists to not only uncover fossils but to simulate movement, reconstruct musculature, and visualize behavior, bringing the long-extinct world vividly to life. Every discovery, big or small, contributes to a larger tapestry. Individual bones, footprints, eggs, or nests are pieces of a complex puzzle stretching across continents and millions of years. Each excavation site, whether a single isolated fossil or a bone bed with dozens of individuals, provides a window into prehistoric ecosystems, predator-prey dynamics, reproductive strategies, and environmental pressures. Together, they allow us to walk in imagination alongside creatures that ruled the earth long before humans appeared. Education and outreach extend the impact of fossil discoveries. Students, enthusiasts, and communities around the world engage with paleontology, learning not only about dinosaurs but also about geology, evolution, and scientific methodology. Fossils inspire curiosity, critical thinking, and an appreciation for the deep history of life on Earth. In this way, every dig, every discovery, becomes part of a larger mission to connect humanity with its planet's rich, ancient past. Ultimately, research and discoveries in paleontology are as much about storytelling as they are about science. Fossils are the narrative threads, and paleontologists are the interpreters, reconstructing life, behavior, and environment from fragments. From the first discovery of a fossilized tooth to the reconstruction of an entire skeleton, each step reveals a world that is at once alien and astonishingly familiar, a world governed by the same principles of adaptation, survival, and evolution that continue to shape life today. The pursuit of understanding dinosaurs is a journey without end. Each expedition, each careful brushstroke across rock, each laboratory analysis, adds depth to our knowledge, illuminating creatures that lived, thrived, and disappeared millions of years ago. Paleontology bridges time, geography, and imagination, connecting us to a long-lost world that remains as captivating and mysterious today as it was in the age of the dinosaurs. From myth to museum, how dinosaurs captured human imagination, myths, and modern exhibitions, long before the first fossil was ever carefully brushed from the rock, dinosaurs were already stirring human imagination. From the whispered tales of monstrous beasts lurking in shadowy valleys to the fantastical illustrations of the 18th and 19th centuries, these creatures captured our collective fascination. They were more than bones in the earth. They were symbols of power, mystery, and the unknowable past. Humans projected myths onto their forms, imagined them as dragons or giants, and wondered what terrible or wondrous forces had shaped the world in which such creatures once lived. Early interpretations of fossils were often intertwined with legend. Massive bones discovered in remote regions were sometimes thought to belong to giants, dragons, or other mythical creatures. In China, large fossilized bones were called dragon bones and were used in traditional medicine, while in Europe, partial skeletons inspired tales of ancient monsters. The imagination filled gaps in knowledge, creating a bridge between the mysterious remains of prehistoric life and the human need for narrative and understanding. As science progressed, the myths began to merge with empirical observation. By the early 19th century, fossilized bones were systematically catalogued and studied, and the concept of dinosaurs as a distinct group emerged. Richard Owen, who coined the term Dinosauria, envisioned them as magnificent creatures that walked the earth millions of years ago, distinct from both reptiles and modern mammals. His work transformed mythical interpretations into a framework grounded in anatomy, evolution, and scientific inquiry, while still leaving room for wonder and imagination. Illustrations and early reconstructions played a pivotal role in shaping public perception. Artists and scientists collaborated to imagine how dinosaurs moved, fed, and lived. These depictions were often dramatic, ferocious predators leaping from trees, herds of giant herbivores thundering across plains, but they captured the essence of a lost world. Museums began to display fossilized skeletons, allowing the public to see, for the first time, the true scale and majesty of these creatures. A single mounted T. Rex or Brachiosaurus became a symbol of deep time, evolution, and the extraordinary diversity of life. Exhibitions transformed paleontology into an experience, bringing stories of prehistoric life to life in ways that textbooks alone could not. Carefully mounted skeletons, dioramas depicting natural environments, and interactive displays allowed people to immerse themselves in the Mesozoic world. Fossilized footprints, nests, and eggs added depth and realism, illustrating behavior, reproduction, and social dynamics. Museums became a space where science and imagination intersected, where visitors could marvel at both the evidence of the past and the stories it inspired. Public fascination grew alongside media depictions. Books, films, and documentaries portrayed dinosaurs in a variety of lights, from terrifying predators to gentle giants, from scientifically accurate reconstructions to imaginative reinterpretations. Popular culture both reflected and reinforced scientific knowledge, creating a feedback loop where fascination drove research, and research fueled imagination. Each new discovery, from feathered theropods to enormous sauropods, captured headlines and inspired wonder, connecting millions of people to a prehistoric world once thought unreachable. Myths were not entirely abandoned, however. Even as paleontology advanced, dragons, sea serpents, and monstrous reptiles remained embedded in cultural narratives. Fossils inspired artistic interpretations, literature, and folklore, demonstrating the enduring power of these creatures to stimulate the human imagination. Science and myth intertwined, with each discovery challenging old ideas while feeding the imagination with new possibilities. Modern exhibitions have expanded these experiences, combining technology with fossil evidence to create immersive journeys through time. Virtual reality, life-sized animatronics, and interactive touchscreens allow audiences to explore habitats, observe behavior, and understand ecosystems. These tools illuminate complex ideas, such as predator-prey dynamics, migration, and evolution, while maintaining the sense of awe that dinosaurs naturally inspire. Museums are now both classrooms and theaters, blending education with narrative to engage audiences of all ages. Educational outreach extends beyond museum walls. Documentaries, online resources, and field experiences invite people to engage directly with the science of paleontology. Fossil digs for students, citizen science projects, and interactive platforms allow a more intimate connection with the process of discovery. These experiences bring people closer to the past, transforming the act of learning into a journey of exploration and wonder. The legacy of dinosaurs in human culture is profound. They embody both the tangible evidence of evolution and the boundless scope of imagination. They remind us that life has existed in forms far stranger and grander than we can fully comprehend, and that our curiosity can bridge the vast gulf of time. Fossils are the anchor, but myths, art, and modern exhibitions are the wings that allow these ancient creatures to live vividly in our minds. From the first fossil discovery to the latest museum installation, dinosaurs have continuously inspired humans to question, explore, and imagine. They have shaped our understanding of natural history, influenced art and literature, and connected generations across continents through a shared fascination with the deep past. In every diorama, every mounted skeleton, and every animated reconstruction, we witness a dialogue between science and imagination, a conversation that spans millions of years, from the Mesozoic to the present. Even today, the fascination continues. Feathered dinosaurs, newly discovered species, and revolutionary interpretations constantly redefine what we know. While captivating documentaries, films, and exhibitions draw millions into the prehistoric world, dinosaurs are no longer just fossils, They are cultural icons, scientific achievements, and enduring symbols of curiosity, imagination, and the relentless drive to understand life on Earth. Dino legacy, birds, feathers, DNA traces, and their impact on modern science and culture. The story of dinosaurs does not end with extinction. In the soft brush of forests, the skies above plains, and the DNA of modern creatures, their legacy endures. Dinosaurs are not just a chapter of deep time, they are alive in the living world, etched into feathers, bones, and genes, leaving traces that shape our understanding of evolution, biology, and the interconnectedness of life. Their impact resonates in science, culture, and even the way we perceive the natural world. Birds, the most visible inheritors of dinosaur heritage, are living dinosaurs. This realization, hard-won over decades of research, transformed our understanding of evolutionary continuity. Theropod dinosaurs, with their feathers, hollow bones, and intricate behaviors, provided the blueprint for modern avians. From the tiniest hummingbird to the towering ostrich, every bird carries within it the echo of a lineage that stretches back over 160 million years, a living bridge connecting the Mesozoic to the present. Feathers themselves are more than just adornment or tools for flight. Fossil evidence reveals that feathers initially evolved for insulation, display, and sensory purposes long before they were used for aerial mastery. Plumage patterns, colors, and structures preserved in fossils illuminate behavior, courtship, camouflage, and social signaling. Feathers are a testament to evolutionary ingenuity, demonstrating how small adaptations can drive survival, diversification, and ultimately, the emergence of entirely new forms of life. DNA traces, though rare, offer a molecular window into the past. Proteins and fragments preserved in exceptional fossils hint at genetic continuity. Evolutionary relationships, and even the physiology of extinct species. Molecular paleontology complements anatomical and behavioral evidence, allowing scientists to reconstruct growth rates, metabolic strategies, and evolutionary pathways. These biological breadcrumbs connect extinct species to living descendants, deepening our appreciation of life's intricate continuity. The cultural impact of dinosaur legacy is equally profound. Dinosaurs inspire art, literature, film, and education, bridging scientific discovery with imagination. The recognition that birds are modern dinosaurs reshapes narratives, allowing us to see familiar creatures in an entirely new light. Every feathered bird that takes flight carries the silent story of its ancestors, connecting us to the ecosystems, climates, and evolutionary dramas of the Mesozoic. Scientific methods continue to refine our understanding. Comparative anatomy, cladistics, and molecular techniques trace the relationships between extinct and living species. Fossilized feathers, skeletal structures, and eggs provide a layered understanding of behavior, reproduction, and adaptation. Each discovery, whether a new feathered dinosaur or a DNA fragment, adds depth to the narrative, demonstrating that dinosaurs are not merely relics of the past but active participants in the ongoing story of life. Even in human culture, the legacy of dinosaurs manifests in symbolism, curiosity, and education. Birds, as descendants of theropods, serve as living reminders of survival, adaptability, and the passage of deep time. Their behaviors, from nesting strategies to migratory patterns, echo ancient strategies honed over millions of years. By observing birds, scientists and enthusiasts alike gain insights into behavior, ecology, and evolution, revealing how ancient traits persist and influence modern life. Dinosaurs' impact on science extends beyond paleontology. They illuminate evolutionary mechanisms, patterns of adaptation, and the consequences of mass extinctions. Understanding how certain lineages survived, transformed, and gave rise to modern birds informs conservation biology, ecosystem management, and our understanding of resilience in the face of environmental change. Dinosaurs' legacy is both a window into the past and a guide for interpreting life in the present and future. The aesthetic influence of feathers, colors, and forms continues to inspire fashion, design, and artistic expression. The vivid reconstructions of feathered dinosaurs have redefined imagination, blending science with art to create creatures that are scientifically accurate yet breathtakingly beautiful. Exhibitions in museums, films, and digital media celebrate this fusion, allowing audiences to appreciate the elegance, complexity, and enduring presence of dinosaur heritage. Feathers, bones, and DNA are more than remnants, they are storytellers. They narrate tales of adaptation, survival, innovation, and continuity. By studying them, scientists uncover patterns of growth, reproduction, and behavior, connecting extinct ecosystems to contemporary environments. Each discovery reinforces the principle that life is interconnected, that species are threads woven into an intricate tapestry spanning millions of years. Dinosaurs' enduring presence in scientific research, popular culture, and living species demonstrates the profound reach of their legacy. They remind us that extinction is not absolute, that life persists through adaptation, and that the past informs the present in ways both subtle and spectacular. From the fossilized feather of a small theropod to the majestic flight of a modern eagle, the story continues, written in biology, culture, and imagination. Through every observation, every flight of a bird, and every fossilized feather, dinosaurs whispered the story of evolution, resilience, and wonder. They bridge time, connecting the deep past with the living present, reminding us that life is an unbroken continuum, rich with lessons, inspiration, and beauty. In their feathers, their DNA, and their descendants, the age of dinosaurs remains alive, shaping science, culture, and the way we perceive the natural world today. Rise, Fall of Dinosaurs, Round 2. Final reflection on their 165 million year reign and the lessons for Earth's future. Imagine Earth hundreds of millions of years ago, a planet in constant motion, teeming with life forms both strange and magnificent. In this vast, evolving landscape, dinosaurs rose to dominance, carving out ecosystems, shaping climates, and influencing the evolutionary trajectory of countless species. Their reign lasted approximately 165 million years, a span of time so vast it defies ordinary comprehension, yet within that immense stretch, they lived, thrived, adapted, and ultimately vanished, leaving lessons encoded in stone, fossil, and gene. The rise of dinosaurs was neither sudden nor simple. Emerging in the early Triassic, they occupied niches left vacant after the Permian mass extinction, seizing opportunities presented by a recovering world. Early theropods, sauropodomorphs, and ornithischians spread across Pangaea, exploiting new territories, climates, and resources. Their anatomy, behavior, and physiology evolved in response to challenges, from predation to environmental shifts, creating a dynamic interplay between species and ecosystem. The Earth of their early reign was a complex stage, hot in the interior, cooler at the edges, shaped by tectonics, seas, and winds, a world in which dinosaurs learned to master survival. Throughout the Triassic, Jurassic, and Cretaceous, dinosaurs diversified into an astonishing array of forms. From the towering Argentinosaurus stretching over 30 meters in length to the agile Compsognathus sprinting across fern-covered plains, they explored the extremes of size, behavior, and adaptation. Feathers, crests, horns, and claws became not only functional tools but signals in social interactions, courtship, and defense. Evolutionary experimentation flourished, with lineages branching, converging, and innovating in parallel, producing creatures that were both alien and familiar to our understanding of life. Predator and prey co-evolved in an intricate arms race. Apex theropods like Tyrannosaurus and Allosaurus drove the evolution of defensive adaptations in herbivores, armored plating, spikes, horns, and herd behavior. Each encounter shaped morphology, behavior, and ecology, creating ecosystems balanced by interaction, not chance. Migration patterns, reproductive strategies, and social structures were refined over millennia, demonstrating that life on Earth is an ongoing negotiation between survival and opportunity. Yet, as dinosaurs rose, Earth itself remained unpredictable. Continental drift fragmented Pangaea into distinct landmasses, creating isolated evolutionary laboratories where species diverged, adapted, and evolved in parallel. Climate changes, sea level fluctuations, and volcanic activity constantly reshaped habitats. Dinosaurs thrived because they could adapt, exploit resources, and diversify, but even their remarkable resilience could not prevent the pressures that eventually accumulated toward decline. The fall of dinosaurs was as dramatic as their rise. The end Cretaceous extinction, approximately 66 million years ago, was the culmination of multiple catastrophic events: asteroid impact, massive volcanism, climate upheaval, and ecological disruption. It was a final test of adaptability, one in which even the most formidable, specialized, and widespread species could not prevail. In this extinction, we see the fragility of dominance, the limits of adaptation, and the reality that even the rulers of millions of years are subject to the whims of planetary change. Yet their influence endures. The disappearance of non-avian dinosaurs reshaped Earth's ecosystems, opening ecological niches for mammals, birds, and eventually humans. Birds, as living descendants of theropods, carried the legacy of dinosaurs in their feathers, flight patterns, and behavior. Genetic traces, morphological adaptations, and evolutionary strategies persist, illustrating that extinction is not the end of influence but a transformation of life's tapestry. The story of dinosaurs also provides profound lessons for understanding our planet. Their rise demonstrates the potential of life to adapt, innovate, and flourish across diverse environments. Their fall reminds us of the vulnerability of even dominant species to rapid environmental change, asteroid impacts, or volcanic cataclysms. Fossils, geology, and evolutionary patterns offer warnings and insights into resilience, adaptability, and the interconnectedness of ecosystems, lessons increasingly relevant in an age of climate change and biodiversity loss. Observing the 165 million year narrative, one realizes that dominance is not permanence, innovation is not immunity, and adaptation is only effective. Within the limits of environmental stability, dinosaurs mastered life for epochs, yet their extinction emphasizes that survival requires both resilience and flexibility, qualities that continue to govern life today. The history of Earth's ancient rulers reminds us that life is dynamic, fragile, and endlessly inventive, a story written not just in fossils but in every living organism, in every ecosystem, and in the ongoing evolution of the planet. Even in our modern age, their shadow looms large. Scientific research, museums, documentaries, and culture immortalize their forms and stories, ensuring that the triumphs, struggles, and ultimate demise of dinosaurs continue to inform, inspire, and fascinate. They remain a lens through which we explore adaptation, survival, and ecological interaction, offering both awe and humility in understanding life's long journey. From the earliest Triassic beginnings to the catastrophic events at the close of the Cretaceous, dinosaurs exemplify the cyclical nature of life on Earth: emergence, dominance, adaptation, and extinction. Their story is a chronicle of resilience, innovation, and the relentless march of evolution. By studying their rise and fall, we gain perspective on the forces shaping life, the fragility of ecosystems, and the profound responsibility inherent in stewarding the world's biological legacy. In their bones, footprints, feathers, and DNA, the dinosaurs whisper lessons across millions of years, about survival, about change, and about the fleeting yet extraordinary opportunity to leave a mark upon the earth. Their reign may have ended, but the echoes of their existence continue to shape life, science, and imagination, a timeless narrative of Earth's deep history, the marvels of evolution, and the enduring impact of life's extraordinary journeys.